Hello and welcome back to Dr. Logic Awkwardly Does Logic. We're going to put together all of the pieces that we have been dealing with the entire process for proving the completeness of S5. We already know how the theorem works. We had our two lemmas, everything. But what I'm going to do is in this video, I'm going to pick an arbitrary formula and walk it through every single step of the process to determine if it is a theorem or not. If it's not, I'll give a counterexample. If it is, I'll give a proof. We'll give one example in this video, one in the next video. One of them will work, one of them will not. Which is which? Stay tuned and find out. So I've got to get the whiteboard because we are going to need a lot of this. We're going to start with an entirely arbitrary formula. We are going to do necessarily, possibly, either possibly P or Q implies not P, implies possibly Q implies not possibly P. This is an arbitrary formula. Is this a theorem of S5? Step one. If you calculate the modal degree of this formula, you'll see that it is of modal degree 3, because here we've got first degree formulas. These two are within the scope of another diamond, so this is second degree. All of this then is within the scope of two more, so it's not a first degree formula. However, we know that in S5, every formula that is not a first degree can be reduced to a first degree formula. So that's what we're going to do first. Reduce to first degree. So, first thing to do is to eliminate the implications. What I will do is I'm going to just copy this formula down. And let me tell you, this is the point that you need to pay the most attention. Taking the formula that you've been given to start with and copying it down accurately. I can't tell you the number of times that I have seen mistakes on homework assignments or in exams where somebody just didn't copy down the right formula. So let's make sure that we've got this absolutely correct. Among other things, what I will do as soon as I've copied it down is I'm going to double check my parentheses to make sure that everything is matched. So that one matches that one. That one matches that one. That one matches that one. Oh, no, I've got a lost parenthesis somewhere. Let me check my notes and find out where. Nope, I had one too many. We are going to get rid of that one right there. There we go. Always worth double checking. It's the silly mistakes that are going to cost you. So we're going to convert our implications to disjunctions. So we've got these here. So this becomes not possibly Q or not possibly P. And here we've got not Q or P. And then this is that. There you have it. We've eliminated our implications, and so now we've got just the easy things left. The next thing to do is to apply modal interchange. So every time you have a negation, drive it through so that it is on the right side of all of your modal operators. So this becomes possibly, necessarily, not diamond P or not Q or P, or possibly, necessarily not Q or necessarily not P. Now we've got negations that are over the scope of disjunctions, so we can apply De Morgan's only on this half. So we've got a negated disjunction. This becomes not possibly P and not Q or P. I'm just going to say or the same because that doesn't change. And then we can do some modal interchange again, because this not diamond, we want to become a box not, so necessarily not P. And again, another negation over disjunction. So let's convert this into not Q and not P through De Morgan's. And then I'm just going to get rid of that double negation right away and quick put in that parenthesis that I dropped. So now we have modalities and either disjunctions or conjunctions. All of our negations are attached to atoms. So this means that we can do some distribution of the modalities over these. So first, I'm going to take this box and distribute it over this conjunction, which we know that we can do from K principles. So we've got necessarily not P, and necessarily Q and not P. But now we have to go over here. Now remember, generally you can't distribute a diamond over a disjunction, but you can in S5 when you have a modalized disjunct. So this will then become, let me just make sure that I get this correct. This will become over here, possibly, necessarily, not Q, or necessarily, not P. Now, again, I've got another box that can be distributed over this conjunction. So we've got necessarily, or sorry, possibly, necessarily not P, and necessarily Q, and necessarily not P. Now, just to make things a little bit easier, I've dropped this internal set of parentheses because conjunction is commutative. We don't need to have the internal ones there. Finally, we've got this last possibility over here. Again, possibility doesn't normally distribute over conjunction, but it does when one of the conjuncts is modalized. So this allows us to, actually, did I do this in the way that I want to do? I actually want to distribute that diamond before I distribute the boxes. So let's just erase that for now and go back so that we can get possibly necessarily not P, and necessarily Q and not P. Because then I can do the distribution of the necessity over this. And that just makes things, makes things easier, but it also helps if I do it properly. And then that disjunction doesn't change. So now we have all of our modalities and our negations are all attached to atoms. The next thing that we do is just reduce these iterated modalities. So everything that is not the rightmost just gets deleted. So we are going to delete these, and we're going to delete that one, and then we end up with necessarily not P, and necessarily Q, and necessarily not P. So we've got a redundant conjunct in there. Or necessarily not Q, or necessarily not P. This is in first degree. Step 2 is to reduce to ordered modal conjunctive normal form. Now I'm going to get a new whiteboard for that, because we're gonna need the space. So the formula that we are now at is necessarily not P, and necessarily Q, and necessarily not P, or necessarily not Q, or necessarily not P. So we want to convert this into ordered modal conjunctive normal form. The first thing that we are going to have to do is to distribute the disjunction over the conjunction. Now, for this purpose, I actually am going to group these back together so that we just have a conjunct that has, we've got a conjunction that has 2 conjuncts. This will make everything easier. So we're going to take this and distribute it over this conjunct and to this conjunct. So we distribute disjunction over conjunction, and what we get is the first conjunct, or necessarily not Q, or necessarily not P, so the disjunction on the other side. And this gets conjoined to the second conjunct, necessarily Q and necessarily not P, or necessarily not Q, or necessarily not P. So now we've got a conjunction here, but we got some extraneous parentheses that we don't need. We can get rid of these. Oops, That was a bit too much. Let's get the box back in there. And that one. So there we go. We've got a conjunction between necessarily not P, or necessarily not Q, or necessarily not P. And then we can do distribution one more time over here so that we have necessarily Q, or necessarily not Q, or necessarily not P, conjoined to necessarily not P, or necessarily not Q, or necessarily not P. Let's just copy this down so that we've got everything. So what we have is we have a conjunction of 3 conjuncts, 1, 2, 3, where each one of these is a series of disjunctions where everything is either an atom, or an atom with a box on it, or an atom with a diamond on it. And in fact, we only have boxes. So now we can perform the test, because this is in ordered modal conjunctive normal form. We've got all of our box formulas all lined up together. So we perform the test. Let's start with conjunct 1. And we have 3 different disjunctions that we make, one for each of these necessity claims. The first one is the degenerate disjunction not P. The second is the degenerate disjunction not Q. And the third is the degenerate disjunction not P, because we don't have any diamond formulas to be disjoining to. None of these are tautologies. Therefore, conjunct 1 fails the test. We don't need to test either of these other 2 conjuncts, because as soon as one conjunction has failed, the entire conjunction has failed. So now what we need to do is we need to construct a countermodel to show that this formula is in fact not valid on the class of reflexive, transitive, and symmetric frames. So we are going to have, let me make sure that we get this right. So we're going to have a world. It's got to be reflexive, because this is reflexive, transitive, and symmetric. And all we need is to have something that falsifies each one of these. So we can make P false, and we can make, we need to make both of them true, because we want the negations to be false. So P is true and Q is true. Then these are both going to make not P false, not Q false. And then we can just kind of ignore this one because it's the same as the other one. We could also, if we just wanted to be careful, make these 2 atoms false, or 2 atoms true at different worlds. So I can make Q true over at this world. And then these need to be symmetric. We don't have enough to really worry about transitivity. This is an S5 model. It makes both of these true. So that means not Q is false. This means not P is false. This means necessarily not P is false, because this world can see a world, namely itself, where it is false. This world can see a world where it is false, namely itself. But then this world can also see a world where Q is false. This means we've got necessarily not Q false over here, necessarily not P false over here. And then from this, you can build up the falsity of each of these. So every single one of these disjuncts is false at this world. So this means that necessarily not P, or necessarily not Q, or necessarily not P, this is also going to be false here. And therefore, all of this conjoined to this will be false, etc., etc., etc. I'm not going to go through the rest of those steps, because basically what it would be is just going through everything that I had already done in the opposite direction. So back to our original question. Is this a theorem of S5? The answer is no. And there you have it. Step by step from an arbitrary formula that I just sat and wrote down, walking it all the way through to determine it's not an S5 theorem. We cannot prove it. We can give a counterexample for it. Isn't that cool? So now you know what you're going to get in the next video. I'm going to do an example that works just so that you've got a bit of a contrast, but you can try it yourself. Just write down any random formula and do the procedure and see what you get. If you've got any questions while you're doing it, feel free to leave them in the chat and I will get back to you. Until then, take care. Cheers.